Alright, so this lab is called Simple Harmonic Motion. It actually has three parts, where two are kind of connected. The first and second part have to do with a mass hanging from a spring. So let's talk about the materials list. Out of your kit, you should have this weird looking spring. Now how do you mount that or secure it to a table? Well, what we did was we hooked a pen across there and we just used, regular old Christmas tape, and we secured the pen to it and looped that around so it's nice and held on the side of the table. You want it up high enough where you can hang onto the meter stick, or hopefully you have that in your kit, and the meter stick, and I kind of like to have that even secured to the table somehow so that it stays also in a way where I can look at and take really good measurements of how much the spring is elongated. In your kit you also have this 250 gram slotted mass kit, and the big mass that you want is this 50 gram one that's the actual acting as a hanger. So the hanger itself is 50 grams. Now this spring is a little interesting. I don't know in your kit whether or not the spring will do this, but without it, it's really kind of tight. So it's going to be significant that we got to make sure that it wiggles a little bit. I actually stretched my arm a little bit, but I'm scared to give you that advice. So what you want to do is just make sure you have enough weight on there, and I think the 50 is enough weight on there, where for now, for the first part of the lab, you're going to ignore that 50 gram mass. You're going to start with the 50 on there and never think that the 50 is on there. In other words, zero in either the bottom of the mass, or if you want to choose another reference point, the top of the hanger, wherever you want to do. I've had people take a little wire and tape it to the top of the hanger and have a wire go sideways so that it's actually being read easily on the meter stick. Whatever, you need to know the original position of the mass. But again, you want to ignore this 50 gram mass to begin with, because it's used just to make the spring stretch enough to actually have a little bit of an oscillation to it. Alright? Then, when you actually are doing the lab, then you're going to add possibly 20 grams at a time by slipping them over the top and then measuring the change in length. Did you hear what I just said? The change in length from where it was to where it is. Subtract those two numbers and you have the elongation. That's the key. So part one of the lab is to actually find what's called the spring constant. I know you all read your book, so you know that the spring constant from last semester is the relationship between the force hanging, that's the weight, so you got to multiply this by 9.8 after you've changed it to kilograms, so the force or the weight versus the elongation. And you're actually going to graph this so you can get that spring constant from the slope of the line, like you hopefully did last semester if you took this course last semester, or you took 118 somewhere else in your lifetime. So you're just going to keep adding these masses and measuring the elongation, adding these masses, measuring the elongation, adding the masses, measuring the elongation. Make a nice table of the masses, which then is just going to be transformed into the force hanging. And when you graph force and the elongation, you end up getting the spring constant from the slope of the line. If you graph it correctly, you should have the elongation on the y-axis and the force on the x-axis, because the elongation depended on the force. And in that case, the slope of the line will be 1 over the spring constant. So don't forget to get that right. Spring constant is what you need for the second part of this lab. Okay, now let's talk about part 2 of the Simple Harmonic Motion lab. There's 3 parts. First part we already did, hopefully, is to find K, the spring constant, by doing enough different masses hanging in order to get a graph where you get the spring constant. Now we know K in our minds, and what we're going to do is compare the equation with the K in it to actual data that we take. So here's what we do. We need a stopwatch. I don't have a stopwatch, so I had to download an app on my smartphone, and the app was appropriately named Stopwatch. And
Easy Stopwatch.
Easy Stopwatch. So if you got a smartphone, download a stopwatch feature if you don't have a stopwatch or a watch that has a stopwatch feature. Alright, now we know K for this thing. So zoom down here a little bit and I'll show you that you're going to hang a certain amount of masses on the end of this thing. Now, you're going to do this at least 3 times. 3's fine, but if this is 50, do you remember how we totally ignored this mass before and we zeroed it in with the 50 on it? Now that mass matters. It has inertia. So we're going to have this 50 count now, and we're going to stick, I don't know, Mike, you suggested what, 70?
60.
60? Yeah, so if you put a 50 on there and then another 10,
The hanger is 50, so you're
50.
just adding another 10.
Correct. So 50 plus another 10 would be 60. Now this is going to be really difficult to count. This will be like the hardest part of the lab ever. Is you're going to move this up just enough, and you want to count 10 oscillations. Doesn't matter the amplitude. So you don't have to pull it way down, because if you do, it's just going to bang up against the side and mess you all up. So whether the amplitude, and amplitude means how far away from the middle it is, all right? So it doesn't matter what the amplitude is. It's not part of the equation. I hope that you all noticed that. So moving it up and down just a little or a lot gives you the same period, but we want to time 10 oscillations of that. So that means take your stopwatch and ready, set, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, here's the most common mistake people make. They start counting with the number 1. You have to start counting with the number 0. So you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Otherwise you would inadvertently get 9 oscillations instead of 10, and it messes up your data, and you can't figure out why you got it wrong. It's because we can't count. Start counting at the number 0, okay? So count 10 oscillations.
The amplitude doesn't matter in terms of the formula for frequency, but it does matter. You don't want the spring to clunk against itself, so you don't want to yank the masses down so it's clunking. If you hear a clunk, do it again. Right.
I mean, like, the point being is that if amplitude doesn't matter, why make the amplitude big? It's easier to read when it's big, but obviously you don't want it so big that it hits the top. Okay, and that's going to be more of a factor when the masses are small. So after you do 60, we recommend that you double that. So after 60, then stick in, let's see, that's 70, 90, 110, and then back with this thing. So now we have 120, exactly double the mass. You might want to stop the video right now and think, what would you expect the period to be, or what would you expect the 10 oscillations to be? Obviously, we're measuring 10 oscillations instead of 1 because then it cuts down the error of reaction time. So if you measure 10 oscillations and then divide by 10, you got a better period than you would have if you tried to do it just once. Okay? So see how this is easier to read? And you can go up a little bit higher and have a bigger amplitude if you choose to, as long as what Mr. Carney just said, don't let it clunk on the top. It's the official physics term for hitting the top. Okay? So measure that. So you do 60, we recommend you do 120, then how about 180, and then how about 240? So that would give you a nice 4 different data points, and you can kind of hopefully do a little prediction, if you know the equation, on what you would expect the answer to be. That's all there is to that part of the lab. Alright, this is part 3 of the Simple Harmonic Motion Lab. Simple harmonic motion, if you read your book, is got a very special relationship. For something to undergo simple harmonic motion, like the mass on the spring did, there has to be a relationship between 2 things. Read your book if you don't know the answer to what relationship must be true in order for have simple harmonic motion. All right? So, if you still don't get it, email us and we'll give you a hint. We're not going to give you the answer to that one because you're supposed to be reading your book. So here's the question for part 3 of this lab. Is a pendulum, or does a pendulum undergo simple harmonic motion like the mass on the spring did? Is this simple harmonic motion? Good question. You got to know what simple harmonic motion is in order to get that answer. Alright, so let's change some variables on this thing and talk about that. But first, let me tell you where we got all this equipment. We're using the 50-gram hanger as our pendulum bob, they call it. Where do you get the string? Well, Mr. Carney suggested dental floss, man. It comes up with 240 yards of this stuff. You can spare 1 meter of that. So, get some dental floss. It works great for string. Alright? Then you have to have something to hang it from. Since I just finished my weight room over here, I hung it from this thing that we do chin-ups on. So any kind of device. Now, why is this important? Well, because later in our lab we might want to change the length of the string, and this seems to be a really nice way of quickly changing how long the string is. So that is our suggestion on what you should do. Hang it from something that you can very easily manipulate the length, because later in our lab that's what we're going to be doing. All right? As far as materials is concerned, the only other thing you need is your meter stick if later we need to do the mass, or the length change. All right, so here goes. This is a very different kind of introduction, because what we're going to ask you is 4 questions, 4 hypotheses that we want you to take, and we want you to actually pause the video, take a guess, write down the answer, and then go on to the next hypothesis. So let's do the first one. Here's the question. If I changed the mass on the end of the pendulum, if I changed how much mass the pendulum bob actually had, will it change the period? You understand? The period is the time it takes for one complete oscillation from here to there. Will this period change if I change the mass? I have 50 on there right now. I'm going to switch it and put 100 on there in a second. So pause the video. Not you. No. Pause the video and tell me what the answer is. If I change the mass, does the period change? Pause now. All right, you're back. Hopefully you paused the video and you wrote down the hypothesis. If you didn't do that, you're not getting your money's worth out of this thing. Pause the video and for real, take a guess on that. So what I want to do now is I'll double the amount of mass I have on that thing. Of course, I don't know what I did with the masses. Here we go. I'm going to just add another 50 grams. Now that I think about it, let's do this. Let's observe together instead of you just backing up the tape. Let's tape. I'm still saying tape. All right. Let's try this. 1 Mississippi, 2 Mississippi. Let's try it again. 1 Mississippi, 2 Mississippi. If you want to have a more quantitative way of doing that, use your stopwatch. All right. Now I'm going to double the mass and see what happens to the period when I doubled the mass. Here it goes. Now there's 100 grams on there. 1 Mississippi, 2 Mississippi. Oh, let's try it again. Ready? 1 Mississippi, 2 Mississippi. Boy, I don't see much of a difference. Interesting, eh? So, you might have had an incorrect hypothesis. Your guess might have been that mass did change it. It doesn't. When you read your book and you see the equation that gets developed for the period of a pendulum, you'll see that M wasn't in the equation. Very interesting. All right, let's try another one. What about amplitude? Amplitude is how far away from the midpoint it is. Just like a mass on a spring had a midpoint and you went above and below, the mass on the end of a string or a pendulum has an equilibrium position, and it goes to the left and the right, goes back. I'm giving you hints on what a simple harmonic oscillator is. So does the amplitude matter? In other words, if I start way out here and have a large amplitude compared to a small amplitude, tell me what you think. So pause the video now. Does amplitude matter? All right, we're back. So hopefully you really did pause that thing, wrote down your hypothesis. Let's see. 1 Mississippi, 2 Mississippi. 1 Mississippi, 2 Mississippi. Oh, amplitude doesn't seem to really have much of an effect. Now, we are lying to you. If you read the book well, you'll see that amplitude does have a slight effect. And the reason why it does is because the amplitude is the horizontal distance to the midpoint. But this pendulum is actually going through an arc, if you think about it. So as long as we keep these amplitudes relatively small, it doesn't have a significant enough effect on it to do anything to our data. So remember, when you're actually doing another part of this lab, don't have the amplitude very large, have the amplitude small, and it has negligible effect on it. All right, let's do one more. Does the acceleration due to gravity, in my room it's 9.81 meters per second squared, I'm not sure where it is in yours, but does the acceleration due to gravity, little g if you will, affect the period of the pendulum? In other words, if I did this pendulum at a place or a location where the acceleration due to gravity was greater or less than 9.8, would that affect the time it would take to go through one complete oscillation? Alright, so what I want you to do is take all your equipment and go to the moon for a little bit and pause the tape. Alright, so you can't really do this one. Alright, so what we'll do is just hypothesize this one and then I'll give you the answer when you get back. So pause the tape, pause the video, and tell me what you think is the answer to the question, does the acceleration due to gravity affect the period? Pause now, answer that. Alright, hopefully you really did pause and you wrote down on your lab sheet what your hypothesis was for does gravity, the acceleration due to gravity, affect the period of the pendulum. I'm just going to have to give you this answer because we can't really travel very far to do this. There's some really unique ways some of my students emailed me on ways we really could have done this, and that is have an air hockey table tilted on an angle and have the pendulum over there, so it wouldn't be G, it would be G sine theta for the thing, because it would just be a part of it, so this whole pendulum was swinging on a platform sideways. Or we could go on the Vomit Comet if you could talk NASA into giving you a ride on that airplane that goes through dives. Depending on the arc they take, you could have the acceleration due to gravity mimic Mars or mimic the moon or whatever you want, or 0 G's, which would make a pendulum probably useless, but it's really kind of neat that there is ways that you could actually test this. But let me just give you the answer. Yes, G matters. If we went to the moon where the acceleration due to gravity is only about 1/6 as it is on Earth, this thing would take longer to go through a complete cycle. If we went to Jupiter with this pendulum, and pretend Jupiter has a surface, if we kind of hovered above Jupiter, it's about 2.5 times the acceleration due to gravity than on Earth. This thing would be going with a shorter period. It would take less time to go through a complete oscillation. Okay, got one more. What about the length of string? We're going to actually vary how long the string is. So here's the pendulum with a string that is, I don't know, about 90 centimeters long. So here's the period. Let's try it. 1 Mississippi, 2 Mississippi. What do you think would happen if we took the string length and we actually made it shorter? So we took this string and we just maybe half as long on the string. Pause the video right now and take that guess. Alright, hopefully you're back after writing down what you think would happen to the period of a pendulum if the string length at the actual pendulum length changed. So let's try it. If we go down here like this, it was 1 Mississippi, 2 Mississippi. Alright, and if we could change the length, which I've rigged it up so that Mr. Carney and I can change this length much easier. And then we just kind of wrap that around there, and again it'll hold it without me having to even hold it. Good old friction. Okay, now we have a shorter length. Let's try it. 1 Mississippi, 2 Mississippi. Oh, 1 Mississippi, 2 Mississippi. Oh, this is significantly shorter. Those of you that got that right, I wonder if you got it right because you have in your possession a musical background and you know a metronome is like an upside down pendulum, so the shorter it is, the shorter the string, the shorter the period. Is the relationship exactly direct, or is there a square root out there? Well, if you read your book, you know the answer to that question. Alright, so that concludes our intro.